So today we're going to be covering the third part of our series set of videos, which is going to be covering geometric series. Now, the idea is a geometric series can be summed over an infinite span if the rate is less than 1, meaning what's going on is our geometric series, let's assume that it looks something like this with our x and our y-axis. And -1 means I'm dividing, so it's getting smaller. So if I see a graph come down and down and down and down and down, I can sum that series over an infinite span. What I can't do is I can't sum that same series in reverse and go all the way up, because what's then happening is I'm adding a larger and larger value every single time to this series. So I need it to go down. An alternative to going down is if we have what we call, do this in purple, is a convergent that oscillates, so something that's approaching a value. So let's say I'm going between negative and positive, but what I'm doing is over time, I'm slowly converging at a point where I'm adding less and less and less each time, so I can actually figure out what that is about to equal if I stretch that out towards infinity. What I couldn't do when my number was getting bigger. So let's break down what exactly we're looking at. This is set in sigma notation, which means I have a starting value. So a starting, let's say term. I'm going to take the first term and I'm going to have an ending term above the sigma. So I have where I start, where I stop, and I'm going to have the function rule or pattern. And so an idea, the long form of what we would do with this, we would say, okay, from 2 to 6, I'm going to plug in 2, then 3, then 4, then 5, then 6, and stop, and add them all up. So I would get 1 times 2, starting with 2, because that's where my 2 goes. And I'd add it to 1 times 2 to the power of 3. I'd add that times 1 times 2 to the power of 4. I'd add that to 1 times 2 to the power of 5, and I'd add that 1 times 2 to the power of 6. And I basically plug this number in and increase it by an increment of 1 until I hit that number, and then I stop. And so long story short, this is a long way of doing things. What we want to do is, instead of having to figure out what all these would equal and add them up, is can I reduce the steps? And yes, we can with a finite geometric series. Whether it's going up or down, this is the way we add it. Now what I can't do is I can't make this go towards infinity if my number is going up, because it just doesn't work. What we're going to do is we're going to take the first term, multiply it times the ratio of 1 minus the common ratio to the nth power divided by 1 minus the common ratio. And so let's see if we can't maybe speed things along a little bit. So here's my sequence, 1, 2, 4, and I want to sum it from the first to the 5th terms. Now, we know the fact that if I take this, that would just mean 1 plus 2 plus 4, looks like we're doubling here, so plus 8 plus 16, and so let's actually set that up. 1 plus 2 plus 4 plus 8 plus 16. Let's see, 1 plus 2 is 3, plus 4 is 7, 15. So I know I'm going to get a 31, but let's assume that we're practicing this for a much larger term, like 1 to the 50th. I know I'm not going to be able to add all those up confidently, and I might make an arithmetic mistake. So I want to use this formula right here. So first off, I need to come up with a function rule. And I know from a geometric series, my function rule is my first term times my ratio to the n minus 1. So as I plug in my terms, my first term is 1. My ratio here is I'm multiplying times 2 to the n minus 1. And I'd want to stick that in, but unfortunately that doesn't resemble the form that we have. I'm looking at n minus 1. Well, how do I get that to move to n? Well, let's take a look and see how I would set that up. Well, if I said a sub n is 1 times 2 for the first term, 1 minus 1, so 0 times, that makes sense. But how do I multiply it times 2 one time and get 1? Well, the way that we do is we actually move a step backwards, and we're going to use whatever would be right here and plug that formula in. So instead of multiplying 2, let's divide by 2. So my modified formula is going to be, divide by 2, that's going to be 1/2 times 2 to the n times. And what this allows me to do is that allows me to create a formula to plug in that resembles this general shape. 1/2 times 2 n times. So for my first one, I can plug in a 1. 1/2 times 2 once, it's going to give me a 1. 1/2 times 2 twice is going to give me a 2. 1/2 times 2 3 times is going to give me a 4. It moves us a step back. So writing it, I'm going to say n equals 1 to 5 of my 1/2 2 to the power of n. And again, what I could do is I could write a series of numbers and plug in all these, and that series of numbers would basically be us adding up all these guys. Or what I could do is use my summation right here. And so we know the shortcut would be 1/2 times 2. Nope, I'm using the shortcut right here. So that's going to be my first number in my sequence. So 1 times 1 minus my ratio, which is going to be 2 to the power of n. So from 1 to 5, that's 5 minus 1 plus 1. There are 5 steps that I'm summing. 1 minus 2. Awesome. Let's go ahead and figure out what this is going to be equal to. So 1, 2 to the 5th power, well, that's going to give me 2, 4, 8, 16, 32. So 1 minus 32 all over negative 1. That's going to give me 1 times negative 31 over negative 1. I actually don't need to write that 1, but I'm going to keep it up for right now. So my summation of that formula, n equals 1, 5th power of 1/2, 2 to the nth, is going to be 31. Perfect. And so let's try another round here. This time, instead I'm going negative, positive, negative. I'm going to be oscillating. So in order to find my pattern right here, I'm going to take my first term times my ratio, n minus 1. And don't forget, I'm going to be moving a 1/2 step backwards here in a minute. So I'm going to take equals negative 1. Looks like I'm multiplying by a negative 2. But in reality, I'm saying that if I'm multiplying by negative 2, let's divide by negative 2. So 1/2. Add these up. And again, I know the long way of 1/2 negative 2 to the power of n would be literally to plug in all of these values from 1 to 5. So the long way of doing this would be 1/2 negative 2, 1/2 negative 2, 1/2 negative 2, 1/2 negative 2, 1/2 negative 2. Would be to plug in 1, 2, 3, 4, 5 and see what they get. But I know a shortcut. So I'm going to say, I'm going to take my first term, my true first term, which is going to be a negative 1. I'm going to multiply it times 1 minus the rate, which in this case is -2 to the 5th power, because there are 1, 2, 3, 4, 5 pieces in here, divided by 1 minus the rate. Boom. We're going to see what this gets. So I'm going to bring this around. So -1. 1 minus, let's see, negative 5 times is going to end up being another negative. So minus, let's see, 2 to the 5th power, just like before, is going to be 32. Minus a negative is going to be plus positive. So 1 plus 2 is 3. Minus a negative is going to be positive. So -1 times 33 over 3, or -1 times 11, which is 11. Boom. There we go. So the first 5 terms are going to add up to -11. Perfect. Let's try a few more. If instead of going up, I'm going down, no worries. Times r to the n minus 1. I recognize that I'm dividing by a constant number. So that means my a sub n is 100. Divide by 10. 10 minus 1. But again, I want to just have a regular n, which means my actual formula is, let's see, instead of dividing by 10, I'm going to multiply by 10. 1,000 times 1/10 to the power of n. I'm going to plug that in. And again, we know that this could be done the long way of 1, 2, 3, 4, 5. Could have taken this from 1, 2, 3, 4, 5 and add all these up. But I'm like, hey, there's a lot of chances for small little arithmetic mistakes, meaning I'm going to multiply or divide something wrong. So why don't I just go ahead and say, hey, it's going to be equal to my first term, which is going to be, my true first term is going to be a 100. I'm going to multiply this times 1 minus the ratio, 1/10. To the power of 5 units divided by 1 minus the ratio. Okay? And now, I know this is tempting to use your calculator on this, but one of the things that we want to avoid is we want to avoid calculator when possible, especially when dealing with what we call converging series. So this is getting smaller and smaller and smaller and smaller. It's got to be a giant fraction. Your calculator might actually create a decimal that it's going to round. Again, we want to avoid that if possible. So what I'm going to do is I'm going to take this 1/10, multiply it, or raise it to the power of 5, which means I'm going to have 1 to the power of 5 divided by 10 to the power of 5, which means that's a 1 with 5 zeros. 2, 3, 4, 5. It's 100,000 on the bottom. 1 minus that, so what I want to do is turn that 1 into something, 100,000 minus this. And same thing down here. I'm going to turn that 1 into something over 10, so 10 over 10 minus 1 over 10. So that's going to leave me with 99,999 over 100,000. Yeah, that's good. Divided by 9 over 10, all times 100. I know that's going to be keep, change, flip. So let's write that as 10 over 9. Well, I know that the zeros are going to cancel out. I know that over here I'm going to have 2 additional zeros cancel out. And then all these 9s are going to divide by that 9, which is going to leave me with, let's see, that's going to be 181, 111, divided by 100. Boom. There we go. Now, the issue where we said we're dealing with a finite series is that typically with geometric series, we always have to start with the first term. What I can't do is I can't start at the second term. That's going to either force me to go via brute force method, which means that I'm going to have to sum, let's see, what is this? 128 dividing by 2, n minus 1 times, which means that my formula that I would like to use is going to be working backwards. I want to find that position. So 256 times 1/2 to the n. To the 5. What that could do is that could force me to say 256, 2, 256, 3, 256, 4, 256, 5. 2, 3, 4, 5. Which means 256 divided by 4. We're going to have to bust out the calculator on this one. $256 divided by, let's see, 8. And if I divide it by an increasingly large multiple of 2, perfect. Alternatively, I could say 256 divided by 4 would give me that one. Divided by another 2 would give me the next one. Divided by 2 would give me the next one. Boom. And so I could add all those up. It's going to be 120. But again, this is going to be tedious. So typically the way that you would handle this, especially if they're farther into the pattern, is you would take the sum of n equals 1 to the 5th and take the first 5, and you subtract the sum of n equals 1 to 2 and subtract the first. No, you wouldn't even subtract the first 2. You'd subtract the first. N equals 1 to 1. You subtract the first term. And that would be the way we'd solve that. Again, this is going to take a few steps. So let's just go ahead and set this up and assume that it's going to be equal to 120, because we're not really going to see many of these going forward. So this is going to be, let's see, the true first one. For this one, that would be 128 times 1 minus 1/2. There's 5 ones. So this, it's going to end up being that. And I'm going to subtract this, which is going to end up being a 1 to 1. There's only one piece in that whole equation. This is going to end up being that. And so we just end up doing it twice. We'll get 120. Because in essence, I guess if we really do want to work this out, can't hurt to show you. It's 2 to the 5th. It's going to give me 1/32. Oop. For 1 minus 1/2. See, that's going to be 32 over 32. So 32 minus 1 is 31 over 32. It's going to be 2 over 2 minus 1 over 2. So that's 1 over 2 flipped 2 over 1. So that's going to divide to be a 16 over 1. That's going to divide, let's see, 128 divided by 16. Is going to be an 8 over 1. So I get 8 times 31. It's going to be 248. And I'm subtracting all of this from this. It's going to be 1 minus 1/2 for 1 minus 1/2. Anything divided by itself is going to cancel out. So I'm subtracting 128, which is going to be 120. Perfect. So boop, boop, boop. There we go. And so that's the majority of what we're doing today. There's a challenge, though, at the end. If I want to sum all terms, I want you to take a moment and think, how would you solve that? Now, again, if all you're looking at doing is how to sum a finite series, you're done. You can go ahead and end the video here. But if you want something a little more in-depth, go ahead and take a look at this and see if you can't figure out what the pattern would be for all terms of this sequence. Okay, so what you might have done is you might have said, okay, let's go ahead and let's set up our rule. And you said, okay, a sub 1 times r to the n minus 1. So my first term, I'm dividing by 2 to the n minus 1. But again, you probably even said, I need to go back a step, which means my true 1 is going to be 1/2 to the power of n. And you used that into our summation of n equals 1 to infinity. Okay, so I'm going from 1 to infinity. Now, okay, that doesn't really help me out very much. 1/2 n. Okay, well, I guess that would mean I would have an infinitely large list like we did right here, but I don't really want to write that out, so I have to use the formula. But again, I'm not sure how that infinity is going to work in the formula, because I know my true first term is going to be a 1. I'm multiplying, or I'm subtracting 1/2 n times, which is going to be to the infinitieth power. Okay, well, I'm not really sure what 1/2 times itself infinity times. Well, let's take a look. 1/2 times 1/2, so this is the first power. Second power. Third. Fourth. Fifth. Sixth. What it looks like I'm doing here, if I were to try and graph that, is let's assume that this is 1. I started out 1/2, 1/4. I keep cutting that distance in 1/2 and 1/2 and 1/2. I'm getting lower and lower and lower. But I don't think I'm ever going to actually cross 0. If I cut a number in 1/2, will I ever get something that's negative? No. In fact, if you have a pizza and you split it amongst, even the population of the Earth, if we're splitting it among the billions of people, you'll still get a little piece of pizza, albeit it'll be really, 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 really tiny. If we go out several billion units out, you're getting like the speck of a crumb, but you'll never get nothing. So I won't ever actually get 0, but I'm going to get pretty dang close. So what I'm going to do is I'm going to assume that this is going to approach 0. Okay. So let's see. So I guess that means that I'm going to be looking at this as 1 minus, we said it's not going to hit 0, but it's going to get so close I might as well assume it's 0. Okay, cool. So that literally just canceled itself out. So that means I'm dealing with, let's see, whatever 1 minus 1/2 is. So that's 1 over 1/2, which keep change flip, that's going to be 2. So if I add up infinitely large amount of terms, I get the number 2. Which leads me to my formula. If I have an infinite series, it's going to be a sub 1 divided by 1 minus r. It's going to be the formula that you use. And there you go. So today we're going to be graphing an equation in exponential form. Now, what we've done previously, we've done things like absolute value, we've done linear form, we've done quadratics. Exponential form is similar to linear form in that linear changes at a constant difference, is what we call addition and subtraction. Where exponential form is still a constant change, but it's a constant rate, meaning we're multiplying or dividing. So the only difference is the operation, and we're going to see what that looks like when we do that different operation. The second thing is every graph is going to have what we call an asymptote. An asymptote is when the line is going to approach some value but never quite get there. And so what does that mean? Well, let's take a quick look at exponent rules because we're going to be dealing with a lot of these. We're going to have things raised to the 0th power. So anything to the 0th power is 1, no matter what it is. If I take 100 raised to the 0th power, it is a 1. The second rule is that if I have a fraction, let's say 1/2 squared, what that means is that both the top and the bottom are squared. That works no matter what it is. So a divided by b cubed is going to be a cubed divided by b cubed. And then the last thing is if I have, we've done 0, we've done positive, if I have a negative exponent, so -1, all that means is that the variable or the number is in the wrong spot numerator/denominator wise. So I know that that means that, well, nothing's left up top, so I'm going to put a 1. My a should have been on the bottom. That works. If I have like b to the -2, that just means that b was on the wrong spot. I need to put a placeholder for 1 and put b to the negative, no, not b to the -2, it's now b to the +2. b was in the wrong spot, so I turn it positive and put it on the bottom. That works no matter how you have it. If I have something like, let's say a divided by b to the -3, well, I know that I'm going to do exactly what I did right here and make a to the -3 and b to the -3, which means a is in the wrong spot. A needs to be on the bottom, and b is in the wrong spot. B needs to be on the top. So knowing these 3 rules real quickly will help you a lot with a lot of the work we're about to do in exponential form. So, well, what does the graph look like? Well, the graph has a basic shape of a times b to the power of x. A is the starting height, and b is the growth factor. So if I have an equation, let's say right here, let's say I'm doubling. So each time I take the starting height, which would be my a value of 1, I double it. So 1 becomes 2, 2 becomes 4, 4 becomes 8. It just keeps going up and up and up faster and faster. And this is what we call divergent. It moves away from what we're going to see the other side is going to approach. It's moving away from the asymptote. And if I'm multiplying, I can look at the other direction and say, well, 4 divided by 2 is 2, divided by 2 is 1, divided by 2 is half, divided by 2 is a fourth, divided by 2 is an eighth, is a 16th, is a 32nd. We notice how it's getting smaller and smaller and smaller, but it's never actually going to get onto the x-axis, because can you think of any number when you divide it in half that will eventually give you 0? No, there isn't a number. So this is what we call our asymptote. And I'm going to draw it a little below the line just so you can see that it's there in blue. And we say, hey, y can never be 0. And that's an asymptote. And the idea behind this is even if you have, let's say you have a pizza and you divide it among a larger and larger group of people. Let's say you divide it amongst all the people on the planet. Well, when I take and divide it by several billion, that pizza has gone down from a whole pizza to half a pizza to a quarter to maybe a slice, to half a slice, then you're getting a pepperoni, then you're getting part of a pepperoni. And then by the time we've split it amongst everybody in the population, the amount that you get is so infinitesimally small, it's not even worth eating at this point. We can hardly call it a pizza when you get part of a molecule of a pizza. But you don't have nothing. So you can't have nothing. It's just so small and insignificant, you don't even wait in line. You're like, I'm gonna go find something else. Let me go find something like broccoli. LOL. So let's graph a few of these. So when I'm dealing with this, I know that I have my starting height is 2, and I know my rate of change, R, or I guess I should say my B, is going to be 3, which means I'm multiplying times 3 each time. And again, if I look at the other direction, I'm going to be dividing by 3. So let's build a table to see if we can't prove a few of these rules. So I'm going to go ahead and start. I know my starting height should be 2. Let's see if we can't prove that by plugging in a 0 into the equation. So 2 times 3 to the power of 0. Let's see. Anything to the 0th power I know is 1. So that's 2 times 1, or 2. Did we get a starting height of 2? Yes. Let's plug in a few more. So like 1, 2, 3. So that means 2 times 3 to the power of 1. That means 2 times 3 to the power of 2. That means 2 times 3 to the power of 3. Let's see if we can't notice the pattern again. So that means 2 times 3, which is 6. This is 2 times 9, which is 18. This is 2 times 27, which is 54. And lo and behold, do we recognize that we have a pattern? We're going to do this in green, where we said my rate of change, or my growth factor, is going to be 3 times 3 times 3 times 3. Each time we increase by multiplying by 3. So realistically, if you have your starting point, you can just fill in the rest knowing where it's going to go. You don't actually need to work it out every single time. Likewise, if we do it in reverse, if I want to plug in a -1, a -2, or a -3, I know that we're going to have to deal with 2 times 3 to the power of -1. 2 times 3 to the power of -2. And 2 times 3 to the power of -3. Okay? So when I work this out, I know 3 is in the wrong spot. That must mean that it is 2 times 1/3. Now that 3 has a positive 1. So that's 2 to the 1/3, which is 2/3. Right here, I know I have 2 times 1. The 3 is now a positive 2 on the bottom. So that must mean it's 2 times 1/9, which is 2/9. And for my last one, I know that's 2. Putting the 3 on the bottom, that's going to be 2 times 1/27, which is 2/27. Let's see if we can notice the pattern going in this direction. So if I'm multiplying going to the right, I'm dividing by 3. Notice how my denominator gets bigger. I'm dividing by 3. My denominator gets bigger. I'm dividing by 3. My denominator gets bigger. Perfect. So if you also notice, your denominator gets bigger when we deal with these negative powers at exactly the same rate as the multiplicative factor got bigger going the other direction. Times 3 divided by 3, times 9 divided by 9, times 27 divided by 27. Perfect. So let's graph a few of these values. I got to go up to 54, so how many spaces do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, that's perfect. 9 divided by 6 is going to be 54, so I'm going to do these by 6s. Okay. So I know at 0, I am about a third of the way up at 2. 1, I'm at 6. 18. And then 54, we said, was right on the end here. Go in the other direction. At -1, I am at 2/3, so right there. 2/9, well, I'm even closer. And then at 2/27, I'm even closer. So that kind of looks like it's just a line, but we're going to go with it. And so let's go ahead and say there we go. And I know I have a starting point right here at 0, 2. The other thing that I notice is that my asymptote is right here where y cannot equal 0. Boom. And there we go. We have our first exponential graph. So let's do another one. Now, for this one, what we're going to do, instead of having to build out the entire form, let's see if we can't just use our starting point and our growth factor to kind of manipulate the environment. So I know I have a starting point at -2, and I have a growth factor of 3. So if I build an XY table, I know at 0, I'm going to have a -2. And like what we did earlier, I know I'm going to times 3, times 3, times 3, which means that for 1, that should be a -6. For 2, that should be a -18. And for the 3, that should be a -54. Likewise in reverse, instead of multiplying by 3, divide by 3, divide by 3, divide by 3. Which means I'm going to leave my -2, but I'm going to put it over 3. If I divide by 3 again, I'm going to leave my -2, but that 3 becomes a 9. If I divide by 3 again, I'm going to leave my -2, and that becomes a 27. That's a lot easier to fill out than this. But regardless, if we needed to prove it, the math would be the same. Let's go ahead and let's graph that. So this looks like a flipped version of what we had up there. So I'm going to go ahead and I'm going to say my y is by 6s again. And I'm going to graph some points at 0, -2, 1, -6, 2, -18, 6, 12, 18, and then 54. The other direction, I just get closer and closer and closer to that value without actually touching. There we go. I have my asymptote right here, where my y is not going to get to 0, but it's going to get really, really, really close. And my intercept right there at 0, -2. Perfect. Well, so having seen that, we know that with factors that are above 1, we know it's divergent. We know these graphs are going to spiral off into infinity. What happens, though, if we have a graph with a factor like this, where it's 1/2? How would that actually look? Well, let's see. I know my starting point on this case would be 4, and my growth factor is 1/2. So xy. Let's see if we can't mathematically see what's going on here. So I'm going to start out right in the middle, and I'm hoping that I'm going to get a 4 because my starting value should be a 4. So I'm going to say 4 times 1/2 raised to the 0th power. Anything to the 0th power is 1, so that's just 4 times 1, which is 4. Perfect. Exactly what we expected. So let's try a few other numbers. So 4 to the 1/2 times to the power of 1, 4 times 1/2 to the power of 2, and 4 times 1/2 to the power of 3. 1, 2, 3. Let's see. We know that with powers, they translate in, so that's just 4 times 1 to the 1 over 2 to the 1, which is 4 times 1 over 2, which is 4/2, which is 2. What's going on right here is 4, well, that's 1 squared over 2 squared, which is 4 times 1 over 4. So 4/4 is 1. 1 cubed over 2 cubed. So that's 4 over 1/8. So 4/8 is 1/2. Let's see if that pattern that we had previously held. Well, it looks like when it's a factor smaller than 1, I'm not getting bigger, but I can look at this one of two different ways. I'm multiplying by 1/2. Or I can say I'm dividing by 2. Doesn't really matter which. I divided by 2 or I multiplied by 1/2, which is my growth factor. So multiplied by 1/2 is 1. Multiplied by 1/2, perfect. So I bet you if I multiply by 1/2, I'm going to divide by 1/2 over here, which if I divide by a fraction, what that's really saying is change flip, 2 over 1. That's just multiplying by 2. So I bet you I'm going to double. I bet you I should get 8, 16, 32. But let's go ahead and try this out. So I have 4 times 1/2 to the power of -1, 4 times 1/2 to the power of -2, and 4 times 1/2 to the power of -3. And this is going to get really cramped right here. So that is 4. Now, if I push that in, 1 to the -1 and 2 to the -1, like what I did right here, I know that I'm going to have to flip them. So why don't I just go ahead and flip it and say that's actually 4 to the 2 over 1, which is just 4 times 2, which is 8. That's exactly what we said was going to happen. So why don't I just say this is 4 times 2 over 1 squared, which is just 2 squared. So 4 by 4, which is 16. Also good. And 4 times, let's flip this, 2 over 1 cubed. So that's 4 times, let's see, 2 cubed is 8 over 1. So just 4 times 8, which is 32. So again, that's exactly what we expected to happen. If I multiply by 1/2, I'm going to divide by 1/2 or multiply by 2. Divide by 1/2 or multiply by 2. Divide by 1/2 or multiply by 2. Perfect. So let's see, I have a point at, I need to go all the way up to 32. 1, 2, 3, 4, 5, 6, 7, 8, 9. If I did this by 8, those would need to be by 4s. Oh, that's perfect. So my first point is at 0, 4, 2, 1, half. Okay. -1 is at 8, 8, 16, 20, 24, 28, 32. Boom. So we have this. So I have a graph that looks something like this. 0, 4 right there. But I notice that this time it's not spiraling off into nowhere. It's actually getting closer and closer as time goes on to our value. So our value right here is y can still not equal 0, but it's getting closer. So this is what we call convergent. It's getting closer and closer and closer to that value instead of what we saw earlier, where it was getting farther and farther away from that value as time went on. So this is what we call convergent. Eventually, if we can get out to infinity, maybe we might actually get 0. But I want you to go ahead and pause the video. Try out number 7. We've got a negative and a fraction. Try out number 7. When you're done, unpause it and see how well you did. Okay. So what I know here is I'm going to do this the short way. Now my starting value is -4. Now my rate of change is 1/2. So for my x, y, I know that if I can spot that initial value, I know that as I move forward from 1 to 2 to 3, that is going to be multiplied by 1/2, or I'm going to divide it in half. Multiplied by 1/2. Multiplied by 1/2. So half of -4 is -2. Half of -2 is -1. Half of -1 is -1/2. Halfway done. And on this way, I know that I'm going to divide by 1/2, which is really just saying multiply by 2. I'm going to divide by 1/2, which is really just saying multiply by 2. And divide by 1/2, which is really just saying multiply by 2. So -1, -2. So if I multiply by 2, -8, -16, -32. So let's see if I do this by, I think my last one was 4s. I'm going to have 0, -4, 1, -2, 2, -1. Half is getting closer and closer. If I go this way, it's 8, 16, and 32. Boom. So of that, I have my intercept at 0, -4. And I know this time it's increasing, but it's not increasing all crazy. I know that it's getting closer and closer and closer to this point at 0, but I know y cannot equal 0. It's kind of a weird slash through my equal sign. But the idea is that no matter if it's approaching from above or if it's approaching from below, we know this is still convergent. And there you go. So today we're going to be going over a few aspects of exponential form. Now, a big thing that we see confused in a lot of public literature is the difference between a growth factor and a growth rate. So a lot of what we're going to be going over today is just the difference between the terminology. Because if you're reading over something that's talking about a factor and you see that they're referring to a rate, that's very different than a rate versus a factor. If I have a rate of, let's say, 10%, I know that that's going to give me, if I have a rate of 10%, that means that my rate is actually 0.1. I'm going to take 1 plus that and say, okay, I'm increasing by a rate of 10%. So my b is actually 1 plus 0.1. So my b is 1.1. Again, with most values that are relatively low, it's pretty easy to tell the difference between the two, but again, it's just an important idea that we know the difference between factors and rates. So today what we're going to be going over is the growth factor. If I have a growth factor of 2, I know that my b is going to be equal to 2 of the equation y equals a times b to the power of x. My b is 2. That's all that I need to know. I have a growth factor of 2. Now, conversely, if I have a decay factor, what I know is that my graph is going downwards. So I'm not actually multiplying by 2, I'm dividing by 2. So I'm going to put 1 over 2. That tells me I'm dividing by that number. Now, if I have a fraction and I have a growth factor of 2/5, well, technically that would be a decay factor, but if I have a growth factor of 2/5, my b would be 2 fifths. I'm multiplying by 2/5 each time. So again, technically to have a growth factor, that upper number would need to be higher than 5 because that 2/5 is going to be shrinking. And conversely, if I have a decay factor of 2/5, again, a decay factor means that we are decreasing. We're going to actually be dividing by this. So my b would be 1 over that. So we're going to keep change flip, would be 5/2. So these are actually going to be the terminology. Let's go ahead and fix these. This would be a growth because my b is going to end up being larger than 1, and this would be a decay because, again, my b is less than 1. So a little bit of a terminology screw up there on my behalf. Likewise, if I have a percent increase or a percent decrease, I know my b is equal to 1 plus or minus r. Increase means I'm adding that rate. So my b is just 1 plus 0.02 or 1.02. Nothing too crazy. Likewise, at percent decrease, I'm going to do the exact same thing. My b is 1 plus or minus r. With decrease, I'm subtracting it. So 1 minus 0.18. So b is equal to 0.82 or 0.82. There we go. Now if I have a 112% increase, no different. 1 plus 1.12, that's 112 expressed as a decimal. So my b is 2.12. And if I have a 175% decrease, I know my b is equal to 1 minus 1.75. So my b is equal to negative 0.75. Again, we're going to run into some issues here because if I'm decreasing and I have a negative b, I know what's going to happen with the graph is going to do one of these oscillation things as it slowly zeroes in on a point. And typically we're not going to see behaviors continually decrease if every other time they increase. So again, a little bit of a terminology error here. We don't generally express percent decrease greater than 175% on a continued basis. It's just kind of a one-time shot. If I increase by a factor of 2, well, okay, that means my b is equal to 2. So there's my factor of 2. If I decrease by a factor of 9, well, that just means my b is 1/9. That's a different way of saying decay factor. Same thing if I increase by a factor of 1/3. Well, again, so what we're seeing here is this is where a lot of the ambiguous wording comes into play. We're increasing by a factor of 1/3, which means my factor of 1/3 should be my b, which would make me question, is this actually a decrease? Or if I'm increasing by a factor of 1/3, does that mean that I'm increasing by 1 and an additional 1/3? Would that mean that I'm actually dealing with a rate? And again, a lot of common literature or a lot of public literature where people use terminology like this, it's rather ambiguous and a little confusing because my b could be 1 plus 1/3. So that way I'm getting a number larger than 1 so that I am increasing, because this would signify a decrease. But then again, that would not be a factor of 1/3. That would be a rate of 33%. So again, we're not really sure what's going on with this one. Same thing with this. If I'm decreasing by a factor of 1/3, well, that could mean that my b is just 1/3. But again, if I'm decreasing, typically we look at that as b equals the flip of 3/1. That would be a decay factor. But again, that is going up. And lastly, I could say, am I decreasing by a factor of b could be 1 minus 1/3. So I'm decreasing by a factor, which would mean that would be technically a rate. So again, we're not really sure what's going on if we end up with wording like this. We tend to want to stick to, we have either growth or decay by a factor of 2 or a factor of 4, something very straightforward like this. When we start getting into fractions, kind of ignore the terminology. The factor is 2/5, the factor is 2/5, or if we're going up, the factor is 5/2. percent increase, we typically want to keep those values below 100% because when we start going above 100%, we get with some sort of ambiguous terms. So again, this is one of the big reasons why we go over this terminology so that we can understand what exactly is being said and where we might run into problems if the literature isn't using terms that are properly expressed. So let's take a look at a few examples of said terminology. So with this, we're looking at the population of Greenville. It's got 8,000 people, and it grows by 5.6% each year. Write a function for the scenario. So what we're going to be doing is we're going to be using the formula y equals a times b to the power of x. I know I'm increasing by a rate of 5.6%, so I know I'm not using my factor. I'm going to say y is equal to the starting value of 8,000 times 1 plus 0.056 each year. And so because I want to write this in function notation, I'm going to say, hey, the population is a function of the number of years. So it's 8,000 times 1.056 raised to the yth power, because y is my variable. And so the first few questions are just simply asking, okay, what's the population after 10 years? So we're going to take our equation and say, well, that's going to be piece of 10 is 8,000 times 1.056 raised to the 10th. Now, what we could do is we could say that is 1.056 raised to the 10th power. Write that down and then multiply it by 8,000. What we're going to do is we're not even going to clear the calculator to keep as many decimals as the calculator stores in its memory, and just multiply times 8. So now my population after 10 years has increased to 13,795.2. Then you're going to ask yourself, can I have 0.2 people? No, this one hasn't quite gotten done being born. So it's 13,795 people. Likewise, the same setup over here. It's just going to be a piece of 15. Figure out what the population is after 15 years. So we get 1.056 raised to the power of 15. We get that, but without clearing it, I'm going to go ahead and multiply it times 8,000, so that way I don't have any rounding errors. So I know that my population as a function of 15 years is 18,115.4. But again, that person hasn't been born yet, so it's 18,115 people. One of the big things you want to get in the habit of is making sure you don't actually write out an abbreviated decimal. What many people do is they put 1.056 raised to the 15th power, and they say, that's 2.26. And they'll take 2.26 and multiply it times 8,000. And we'll notice that here, I'm off by a factor of 115 from 80. That's 35 people. So if you're looking at it, it's just a set of numbers, not a big deal. But if we're looking at it as a set of how many people did you predict? Well, that's a lot of people that may end up going hungry due to a rounding error. So we want to make sure we don't clear fractions or clear decimals if we have the ability not to. The same concept applies with money. Now again, the wording in this question might be improved a little bit because simple interest, what that would mean is that I would take $700 and I would figure out what 0.02% is of that $700, which would be 7 times 0.02, 700 times 0.02. Now again, that's $14 a month would be the increase, regardless of how much money you have in savings. So what we really should say here is 2% interest compounded each month. That's going to allow us to say, okay, after the first month, that extra $14 is also earning interest. And that's going to turn this from well, it's just a simple addition to something that's going to be an exponential form. So here I'm going to say we have $700 and I increase at a rate of 0.02, so my 2%, raised to the x power. If I want to turn that into a function, let's say my money, we're going to use an m for that, my money is a function of the number, money is a horrible letter. We're going to say our dollars. So our dollars is a function of the number of months because it's each month. So I don't want an M of M. We're going to say dollars is a function of months. 700 times 1.02 raised to the number of months. Perfect. So we have this. So we're going to ask, how much will the account hold in 2 years? Well, what you might be tempted to do is put a function of 2. But again, let's think about years, months. Let's see, there's 2 years, 12 months in a year. That's going to be a function of 24 months. So I'm going to take 1.02, raise the 24th without clearing it, multiply it by 700. That means after 24 months, we have over $1,000 in our bank account. 96. So this number right here, you haven't quite earned that penny yet, so the bank's not actually going to pay you. They're going to say you've earned $1,125.90 in 24 months. If you leave it in a little longer, we'll give you that extra penny. But if we look at this as a factor of 10 years, well, that's going to be 120 months. So 700 times 1.02 raised to the 120th. So 1.02 raised to the 120th power. Cool, so we're multiplying that 700 times roughly 11. So you have over $7,000. Again, you haven't earned that last penny. So you have $7,535.61. Oh, and there we go.